Half of non-math. Let me begin with a word of prayer here. So I think everything's working, so we'll hopefully the audio doesn't do what it did in calculus this morning. But dearly Father, we thank you for this day. I thank you for these students, and just pray that you help us to understand linear maps today, Lord. In your name I pray, Lord Jesus. Amen. Okay, so we're in section 1.5. Believe it or not, and he's got a lot of I don't know. I don't think I'm going to say everything he says. So what's a linear map?
If you could tilt me just a tiny bit.
Oh.
So I can see the top of the board.
No, not that one. This one. You're all good. Is that?
Yes, perfect.
Okay. So, all right, so definition, a mapping L from E1 to E2 is a linear mapping, right? If L of alpha x plus beta y is equal to alpha L of x plus beta L of y for all x and y in E1 and all alpha and beta in the field of consideration, right? So we can talk about real linear mappings, we can talk about complex linear mappings. The textbook says sometimes L of x is just written Lx. I don't do that usually. I just don't like it. But you know, I'm a glutton for unnecessary parentheses. That's kind of my ninja way. So given a linear map, there are certain characteristic spaces that you can talk about, right? You can talk about the range and, you know, well, let's just talk about some things. So like the, he calls it, I think, the range of L, which I think he just also uses like an RL for. That's, what's that going to be? That's just L of x such that, you know, x is an element of E1, right? That's the range of L. You can also talk about, well, he first of all talks about forward and inverse images. I guess I should really start with that. So L of A is equal to, you know, L of x such that x is an element of A, right? So in view of that language, of course, the range of L is just what? L of E1, right? Yeah, that's the range. And you can also talk about the inverse image of a set, and that's what? That's like, yeah? Yeah, elements in E1 such that what? L of x is an element of B, yeah. So that's the inverse image, that's the forward image. Of course, the forward image is a subset of the codomain, which we are calling E2 here. The inverse image is a subset of the domain. And then he has like a paragraph explaining that without loss of generality, you can assume that the domain of a linear mapping is a vector space. And I'm like, okay, sure, why not? He also talks about the graph. Oh, null space and graph. We should talk about that. So what's the null space? He uses a fancy N. I guess I should use a fancy N. I'm not sure if I can do it. I don't know. Man, I don't have that kind of fancy N in my, it's not in my lexicon. I gotta learn how to write that fancy N. How do you do that? Dang it. Man. I'm just gonna write it like this for now, and I'm gonna add some feet there. Now it's fancy. So the null space of L, that's x in E1 such that L of x equal to 0, right? So it's the set of all points which map to 0. So in terms of inverse image, you could also say that the null space is L inverse of what? The set that just contains 0, right? The inverse image of 0 is the null space. So, yeah. The range, the null space, these are examples of subspaces, right? Because they satisfy the subspace test. If B is a subspace, then the inverse image of B is also a subspace. So like, you can prove that the forward and inverse images of subspaces are subspaces, all right? Those proofs we have hopefully seen in linear algebra, like undergraduate linear algebra, and they are in no way affected by the fact that the spaces that we're dealing with here could be infinite dimensional. Like there's still a subspace test for infinite dimensional vector spaces, no big deal. He also talks about the graph of L, which is a fancy looking G. I'll try like this, and then you come back like that. Man, I just don't have that letter in my, that's not, I'm just gonna have to do like this. G of L. Actually, better yet, you know what I'm gonna do? Graph. There, now everybody knows what I'm talking about. Graph of L. It is the pairs x comma y such that x is an element of the domain of L and y is equal to L of x. I think this purple marker is over. I think this one's done. All right, so the graph is a subset of it's a subset of like E1 Cartesian product E2 for what it's worth. Yeah.
When up top where you say L of A and L inverse of B, can those, I don't think those both can be contained by E1, right? Because you're talking about the codomain.
Well, L of A is a subset of E2. L inverse, that's a 2, yeah.
Okay.
My bad, sorry. I mean,
That's probably on my end.
let's blame Zoom. Okay, so I'm gonna erase all this because none of this is interesting, okay? I mean, excuse me, all of it's very, very interesting, just for another course. Yes? All right. All right, so so here we go, definition. Let's get into something that's a little bit more weighty. E1 and E2 normed linear spaces. All right, mapping F from E1 into E2 is called continuous all right, continuous at x naught, an element of E1, if what? For any sequence x sub n of E1 convergent to x naught, the sequence f of xn, all right, converges to f of x naught in E2, right? I'll get it. Oh, you got it? Yeah, I don't know if you can hear it or not, Audric, but there's a gaggle of giggling girls around here making a lot of ruckus. Must be somebody's birthday or something. Let's see here. Now, like, pragmatically speaking, what we're really saying is that if you're given that the norm of xn minus x0 goes to 0, that implies that the norm of f of xn minus f of x0, right, goes to 0. And to be more clear, this is happening with the norm of E1, right? And this over here is happening in the norm of E2, yeah? Okay. So we're defining continuity here sequentially, all right? And let's see here. If f is continuous at every x in E1, we simply say that f is continuous, okay? Yeah.
Are the norms necessarily like the same? Like,
No.
remember how we had like definitions of norms like max or the norm.
Well, these are different. These are different normed linear spaces. E1 and E2 are like different spaces. They could have different norms.
Okay, so the norms really don't have to be related at all for this to be solid.
No.
Okay.
So a nice example he has. His example 1.5.3 is he just looks at like f. That's a mapping from, let's say, E to the reals, right? Where your mapping is f of x is equal to the norm of x. So, you know, if you have xn going to x naught, then that implies what? Of course, you know, that means that the norm of xn minus x naught, right, is going to 0. That's what that means, right? And so we can consider the norm of f of xn minus f of x naught, and what's that give us? Yeah, so here, and what's the norm on R? Well, the norm on R is actually absolute value, right? So this is absolute value of the norm of xn minus the absolute value, minus the norm of x0, absolute value of all that, right? But, oh yeah, this is exactly our triangle inequality. Remember, we have proved before that this is less than or equal to the norm of xn minus x0. So this is our, I mean, I guess sometimes I call it the reverse triangle inequality, that we can take the norm and we can replace it with something that's smaller than it is the absolute value of the difference of the norms of the elements being added or subtracted. Yeah. But then we know that this, by assumption, goes to 0, right? So thus, f of xn goes to f of x0, which then shows you that this function is continuous at x naught, right? But x naught was arbitrary, right? So the norm is continuous on E. So therefore, so the norm from E to R is continuous. So, yeah. That's good because, what's that?
I need a shift.
Oh, you need, yeah, I gotcha.
Me a little bit. Yeah, a little bit. Sorry.
You're okay. It's, there's not much contrast in this little, oh, there we go. Now I can see it. And I can,
Yeah. Yep. Perfect.
is that good?
I can see it, yeah.
Okay.
Only thing in my way is my own face
Ah,
on the screen.
well, I can't fix your face for you, so sorry about that, but not that kind of doctor. Let's see here.
Probably topology though.
Maybe a topologist.
Yeah. I don't know if my face is a smooth manifold.
Some people definitely look more triangulated after they've been in Hollywood a while. But sorry, I digress. And then theorem 1.5. Theorem 1.5.4, it says, you've got a mapping from E1 to E2. All right. Then the following are equivalent. A, F is continuous. B, F inverse of U is open in E1 for any open U subset of E2, all right? C, F inverse of S is closed in E1 for any closed S subset of E2. So this, of course, you will experience more of in your topology course. All right, these are the definitions of continuous. Well, B is the definition of continuous, the topological definition of continuous, which is a continuous map is a map for which the inverse image of any open set is open. And that defines continuity in topology. Here, we've defined continuity in our context, which is normed linear spaces. We've defined it sequentially. So now you'll be happy, Audric. Now you have full license to use all of your topological arguments in this course, as we have now imported the logical equivalence of the topological definition of continuous. So, see, Audric was trying to use an argument based on inverse image of open is open in a conversation I had with him last week, and I'm like, well, we don't know that yet. And here, we don't know that yet. Now we do, and why do we know it? Well, this is homework for you guys, so haha. That is true. You were trying to do sequences in topology, and it's funny that happens to a lot of us. Like my brother was experienced the same thing because he had like real analysis in high school, and then he gets to topology at Bob Jones, and I think it took him a couple weeks for it to finally hit him. Oh, we've defined open in a totally different way now, So yeah. Now let's look at so this one I'll leave to you guys. I think that the proof of these assertions, like the equivalence of the sequential and the topological definitions of continuity, some days I can just write it down, other days I'll just spin my wheels. So I'm not even going to attempt it. Besides, it's your homework, so you should experience it for yourself. I think usually one of the directions of that if and only if is easy for me. And the other one, I think the only way to disassemble it is with a proof by contradiction. And so those don't always, for whatever reason, come natural to me. I'm more of a constructivist, I guess. But all right. There we go. This one is really cool. I like this one. Because, well, I love linear algebra. And this is just another example of how awesome linear maps are. Check this out. If L from E1 to E2 is linear and continuous at x naught in E1, then L is continuous. All right, let me foolishly look away from the book and see if we can prove this of our own volition, yeah? So to prove that, so we're saying that if it's continuous at one point, it's continuous everywhere. If it's linear. So what we're given, so we know what? If xn goes to x0, right? Then L of xn goes to what? L of x0, right? That we're given. We want to prove it's continuous at some other point, right? So let's say yn go to x1, right? Now x1, and consider what is L of yn equal to?
L of yn?
Hmm?
The sneaky LYN, you know, like you just drop the parentheses.
Oh, no. Oh, this is this is not the sequence. I mean, I am looking. Oh man, the notation. Unfortunately, I'm just actually asking what is L of the particular nth element of the sequence, L of yn. Like we could rewrite that as. Let me just do a little bit of pre-processing here to help us out. So how can I've got this yn. If I do yn equals x1, I could do what? Excuse me. My bad. What if I do yn minus x1 minus x0? What happens then? What would that go to? Yeah, what would this?
Minus xn or x naught? Is that x naught?
Yeah, I think I did it wrong. I should do plus x naught, shouldn't I?
Yeah, it should be x naught. Yeah.
Then that goes to x naught, right? So my point is that if we look at
Oh, just map it.
yeah, L of yn minus x1 plus x0, right?
Yeah, but it's linear.
That is a sequence, right? I can think of this as being Zn, right? And that Zn goes to x naught, right? Which means that L of Zn goes to L of x naught, right? If you like. So the point is that this goes to what?
L of naught.
Yeah, L of x naught, right? By assumption. But what else? L of yn minus x1 plus x naught is actually equal to what? It's actually equal to L of yn, right? Minus L of x1 plus L of x naught, right? By linearity. Using linearity. And so,
That means L of y and minus L of x has to equal 0 at some point.
right, so if we look at this sequence here, right? L of, excuse me. If we look at L of yn minus L of x1, right? I'd like to show that goes to 0 because that would prove that L of yn goes to L of x1. That's what we're trying to prove, right? For an arbitrary sequence which goes to x1, we're trying to prove that the image of that sequence goes to the image of the limit of the sequence. But I have this equation right here, right? And so I can solve that for L of yn, and I get what? Norm of, like, you know, L of yn minus x1 plus x naught, right? Minus what? Minus L of x naught, right?
Yeah, but you can still break it up.
Oh, but that goes to 0 based on what you were just saying, because L of y in minus x1, so it's not minus L of x naught goes to 0 because L of y naught minus x1 plus x naught goes to L of x naught, right?
Mm-hmm. Right, yeah, but I know, let's see here.
Oh, they both limit to x naught.
See, but this this statement right here, this one, that we already agreed on, that means that goes to 0, right? The meaning of this going to that is to say that the norm of the difference goes to 0. Which then shows you that L of yn goes to L of x1, which is what we were trying to prove for an arbitrary sequence yn which goes to x1. So this is basically the trick, is that, you know, essentially this: if you have a linear mapping T, right, and you feed T equal to T of x, right, then well, that's not quite the right way to say it. I'm trying to think. I mean, I've said what I've said, but there's a. No, I'm trying to about to say here. It's not quite right anyway. This linearity condition is just huge, right? Because it allows you to connect points to other points which aren't connected. In some sense, like, knowing how the linear map behaves at one point tells you how it behaves at, well, many, many other points in this sense, you know. I mean, you know, if we know L of x, then we know how the linear map behaves at L of cx, right? Because L of cx is c times L of x, right? So if you know how a linear map works at 1, 0, you know how it works at 2, 0, at 3, 0, at 4, 0, anywhere on the x-axis, right? If you're working in 2 dimensions, but anyway. Listen, the proof on page 27 is, I think, essentially the same, but it's much more like, he's got 3 lines, you know? So it might be better, you know? Anyway, I hope this made sense to you. Now we define bounded linear mapping, all right? So what's a bounded linear map? I gotta go back and get some more juice. My juice is almost out. So to say a mapping is bounded here, I mean, first of all, that sounds a little sketchy to start with, right? Because, I mean, think of any linear map you know from linear algebra. Are the values of the linear map bounded? I don't think so. I mean, because it goes on and on, right? Like I was just talking about, L of Cx is what? Cl of x, right? But C can be as big as you want, so unless L of x is 0. So what does this mean, bounded? So here's the deal. It's called bounded. All right, if there exists alpha greater than 0 such that the norm of Lx, all right, is less than or equal to alpha times the norm of x for all x in E1.
Lx is just L of x. Just difference a squared.
Yeah, you can put parentheses there if you want. I do. There, I feel better about it now. Thank you. Let's see here. So, yeah, what's that saying? It's saying like the output of the linear map. It's like, you know, at most in terms of size, some kind of scalar multiple of its input, right? Yeah. Well, the norm of x doesn't have to be bounded.
Yeah.
Let's fuss with this for a second. Why don't you guys try to solve that? See if you can't absorb. Think about moving the norm of x to the other side. Can you do that? Does that make sense? So try to absorb the norm. So like suppose x is not equal to 0, right? We have the norm of x is not equal to 0, right? So if we look at that, you got 1 over the norm of x, norm of L of x, right? Less than or equal to alpha. But we can rewrite that as the norm of, we can bring that inside, right? So that's 1 over the, well, I can just bring it inside, right? Because it's a positive number. And that is less than or equal to alpha. But what we really have then is the norm of L of x divided by the norm of x, norm less than or equal to alpha. This marker's worthless. All right. So what we really have is that the norm of L of u is less than or equal to alpha for all u in the ball. Well, not even the ball, it's the sphere, right? I guess the notation was sphere of, man, I forget, did the radius come first or second? I can't remember. 0, 1 was it? I really don't remember, but let me just write it out. For all u an element of what? U such that u an element of E1 such that the norm of u is equal to 1, right? So it's the
So wait, why can't you bring the norm of the 1 over the norm of x inside
Yeah, we're assuming that L is linear, right?
Okay.
So C L of x is L of Cx, right? I need to put these markers where they can't hurt me anymore. There, stay over there. Find a new master. Let's see here. All right, so yeah. So it's bounded. Another way of saying this is to say that a linear mapping is bounded is to say that it's bounded on the unit sphere. Okay, so we have to measure boundedness with respect to something reasonable to measure boundedness. In this case, the unit sphere is the go-to object in a normed linear space, right? Because that captures some sense of finiteness in the space, even though the space is generally of infinite extent, right? And there are infinitely many points in the unit sphere. Nevertheless, we can define bounded like so. So theorem, linear mapping all right, a linear mapping is continuous if and only if it is bounded. All right, let's see if we can prove this. I'm gonna follow the book and see where it takes us. Proof. If L is bounded, right, and x sub n goes to 0, then the norm of L of xn, right, is less than or equal to alpha times the norm of xn, right, which by assumption goes to 0, which implies that, L of xn goes to 0, right? What is 0? By the way, it's equal to L of 0, right? So what does this prove? Hence, L continuous where? At 0, right? So it's continuous everywhere since it's linear. So that was not too bad. How about the other direction? So we want to do what? We want to suppose. So we assume bounded, right? So this what I have up here was this part, right? So now we're going to go for this one, and I think we're going to proceed. We're going to assume continuous but not bounded, okay? Towards a contradiction, yeah?
Yeah, wouldn't we just take our bounded viewer proof and just say that's not the case?
Let's see here, bounded theorem proof. What did we prove?
We proved that a linear mapping is bounded if there exists an alpha. But if it's continuous.
Oh no, this is just the definition.
That's a depth, yeah, you're right.
It's just the definition of bounded. It doesn't, I mean, what I have written in black proves that bounded implies continuous. That's true. So what we have written in black here says bounded implies continuous. But now what we're trying to prove is that continuous implies bounded. And so what we're going to do is we're going to I'm going to follow, the book uses a proof by contradiction here. He says if L is not bounded, Um, L not bounded means for each n, for every n in the natural numbers, right? There exists x sub n in E1 such that what? Yeah, the norm of x sub n is greater than, he says n times the norm of xn. Now, let's see here. I think, let me just take a sit down here for a second and let me look at it. So I suppose if it wasn't the case that you could do this, then you could prove it was bounded. You know, if for every n there does not exist an x1 such that that's true, then I suppose. What's that? Yeah, it is the negation of the definition. But there's something else a little bit. I mean, it's being a little bit more concrete too, right? Like it's saying, in particular, it's picking on natural numbers. You can't use any natural number as a bound, right? Well, that's still not quite what it's. It's not exactly the negation of the definition, is it? I mean.
Well, the basis for any alpha greater than 0, there exists an x that e sub 1 such that. But then if it's any alpha greater than 0, and we just choose the naturals, right? And then for each natural, there corresponds an element in the domain. So we generate a sequence that way.
Mm.
Is that right?
I think so. I just, when I look at the definition of bounded, I think about how to negate it. It's complicated.
Well, I mean, if you followed the logic, it would just say you have a L of x over its norm is, no, yeah. That'd be L of 1. It has to be less than a natural number.
L of 1.
Like if you go through the process of the definition, you'd have L of x over its norm is greater than a natural number, but it's the only natural number is 1, and no number is greater than 1 in the natural numbers. There's less than 1, I'm sorry.
I mean, wouldn't the straight negation of it be that it's not bounded if for all positive alpha, such that, for all positive alpha, there.
No, there just doesn't exist a natural number less than 1.
Yeah. That's right.
Divide the norm of xn on both sides, you get 1. Right?
Yeah.
L of 1 is 1. No natural number exists that's less than 1.
Well, are you going back to the proof here? Okay. Yeah. All right. Okay. So yeah. Let's see here. So sorry, I was just thinking about how to Math 200 style negate that sentence, and I don't think this is the strict. I don't think this is the negation of that. I think this is like a logical consequence of the negation.
Yeah.
So that's all I'm saying.
Yeah, no, sorry, yeah, I understand.
Where was I? Oh, then he says define yn. And so I think this is pretty much what you're doing, Audric, isn't it? Xn divided by n times the norm of xn.
Because even if you say the natural number, even if you say 0 is a natural number, then it's automatically bounded.
And what does this give us? This gives us that yn goes to 0, right? And then he says since the norm of L of yn is greater than 1 for all n in the natural numbers. Is that clear? Why is the... I guess that's clear, right? Because if you put that into here, then you get...
If it's 0, it's automatically bounded. Like, that's the only n you can take for 0, is 0.
You get 0. What do you mean by it, though? I'm sorry.
Like, yn
Yeah.
would have to be 0, but if it was 0, it'd be bounded by definition. And there's no other...
Oh, this is also true.
Yeah, so there's no other natural number
But-
less than 1 besides 0.
Okay, but I mean, the logic here, right, is supposing L is continuous, right? It's not bounded. If it's not bounded, then we can construct a sequence. There exists a sequence rather, such that the values of the sequence are, larger than n times the norms of the input, and
Yeah, but the smallest number you could have is it's either undefined because n can only be 0 or 1. So the smallest number n could be is 1, but in that case, 1 is not greater than 1. Because we agree that the sequence over its norm is 1, right?
Yeah, but how do we know that the mapping maps 1 to 1? Not injective. Like you have L of something having norm of 1 being greater than 1, but how do we know that the mapping maps to a natural number 1? I'm sorry, I'm trying to figure it out.
Well, didn't we start with continuous map?
yeah. So I mean, just stick with me for a second here. So then we construct y like this, right? And then clearly this goes to 0 because 1 over n goes to 0, and so we've got a sequence times something that has, like the norm of xn over xn is 1, right? So we can go back to that product of the scalar sequence times the convergent vector sequence theorem that I had to work hard on, and that one, that applied here gives us 0 because this 1 over n goes to 0, so that means that the yn goes to 0 because the other sequence, the norm of it's just equal to 1, identically equal to 1, right? So yn goes to 0, but that's a problem, see, because you can, and I haven't shown the details here, right? But if you feed this, L of yn is what? See, it's the norm of xn over the norm of xn, right? There's an n in there, yeah? And then you've got L of xn, yeah? And so then that is greater than, so that's, I can pull this out here, yeah? Sorry, too many bars. But that is greater than, so this is just 1 over n, right? Because these guys cancel. You're left with that n, and then this, by construction, is greater than n times the norm of xn. Yeah. Which is,
Which then just gives you xn.
yeah. He's got L of yn greater than 1.
Yeah, but now you have 1. Yeah, but now you're saying that 1 over n, L of xn is less than xn, or greater than xn.
Yeah, it's greater than 1, so... But we're
Oh, I'm sorry. Listen, guys, you shouldn't have bought me. I sold you a bill of goods here. This isn't here.
Is xn
That's a 1. See, it's 1 over n times the norm times xn. So the xn is still in the L. Yeah, and then this.
Just bring in the 1 over xn for linearity and leave the n out.
Yeah, there are. I'm not saying you're wrong, Audric. I'm just saying there's more than one way to skin a cat. But you know, either however you want to look at it, that simplifies to 1, right? Well, it's greater than 1. And that's a problem, right? Because this sequence converges to 0, and yet its image, the image of the sequence does not converge to 0. But it has to, because L of 0 is 0, and so this contradicts the continuity, right? This contradicts the continuity of the map. Does that make sense?
That's what Audric's saying, yeah.
So Audric, I'm not saying you're wrong. I can't track what you're. I can't track what.
You both are saying now. Yes, thank you.
Yeah, it's tough shouting in the computer over.
Okay, but anyway, there you go. So a linear mapping is continuous if and only if it is bounded. Now, what he says next, he says, since every linear mapping between finite dimensional spaces are bounded, right? That every linear map, right? Every linear map on a finite dimensional vector space is bounded. Therefore continuous. So does that mean that there are linear maps which are not continuous in infinite dimensions? Is that what he's getting at here? What do you guys think?
Does that mean there are linear maps and not dimensions? There are what?
So every linear mapping which is continuous is bounded and vice versa, right?
Yeah.
And in finite dimensions, this isn't particularly interesting because in finite dimensions, every linear map is continuous and every linear map is bounded.
Yeah.
What about infinite dimensions? Are there linear maps in infinite dimensions which are not bounded?
Well, yeah, because couldn't you map the unit ball? And since the unit ball can't be bounded.
Yeah, I mean, I think you're right, but what's an example, right?
Oh.
Maybe what you just said, I have to think through it, but I mean, I would just draw your attention to the fact that what we just proved here does not assume finite dimensions, right?
No.
This is not a... So let's go on here. I probably shouldn't have erased what was on the top. You guys will remember for me, right? If it's continuous, it's bounded, and vice versa. All right, let's go on. All right, so theorem. If you've got E1 and E2 normed linear spaces, yeah, then we can let B of E1 to E2, what is that going to be? That's going to be L from E1 to E2, such that what? L linear and L, and you got your choices, right? You could either say continuous or you could say bounded. I'll say bounded because he's using B, so it feels kind of bounded, right? Then what? What's the deal with this? Well, he says that this is a normed linear space with the norm of L equal to supremum norm of x equal to 1 of the L of x. And of course he doesn't put the parentheses in because He's cool like that. Hmm. All right. Let's see if we can prove this one. So what is needed to prove here?
I mean, the only thing we're changing is that this norm is not defined by the max, it's just defined by the least upper bound now.
Let's see. So yeah, let's see here. So let's let I guess L1 and L2 be elements of this space, right? And we'd like to show, I mean, so the vector addition is the usual for, we're dealing with functions, so we define vector addition pointwise, yeah?
Yeah.
Okay, scalar multiplication pointwise, fine. And so I would point out that the fact that that a linear combination of linear transformations is again a linear transformation, still true, infinite dimension. It doesn't matter that they're not vector spaces anymore, right? Like you can check that if we have, you know, CL1 plus L2 of alpha x plus beta y, you work it out, right? You've got CL1 alpha x plus beta y plus, you know, L of alpha x, L2 of alpha x plus beta y, and you get, you know, alpha times CL1 plus L2 acting on x plus beta CL1 plus L2 acting on y. You know, I mean, I'm skipping some steps here, but you can use linearity of L1 and L2 and then regroup things, and then voila, you have that CL1 plus L2 is again a linear map, right? So the fact that, so first, for this to be a normed linear space, it has to first of all be a linear space, right? So it's a linear space with respect to this notion of vector addition. Then the real question, the thing that's more technical, is that a norm? So what does it take? What does it take for this to define a norm?
L is 0, then L is almost 0, travel quality, that scalar multiple times it.
Oh yeah. So let's talk about that. How about if the norm of L1, let's say, we just say L. The norm of L is equal to 0. What's that mean? The supremum, right, of the norm of x equal to 1 of the norm of L of x, right?
Gotta be scalar.
Hmm. So what's that tell you? See, what that tells me is that the L of x is equal to 0 for all x in E1 such that what? Norm of x equal to 1, right? And my claim is that if that is true, it has to be the 0 map. Why is that? Well, if we look at L of y, right, and y is not equal to 0, then we can rewrite L of y as what? We can rewrite L of y as L of, 1 over the length of y times, excuse me, my bad. We can rewrite that as the norm of y, right, times y over the length of y. Because